In this video, I'd like to introduce you to some physical or physicsy thoughts about the phase of matter known as solids, or thinking about solid materials. Maybe as a working example, you might be thinking of water molecules in a solid, so that what we're talking about is ice, for example. Okay, so solids, the situation is solids are made out of atoms and molecules or compound structures that are associated with like a network. So the idea is like we have these entities like atoms or molecules really, or compounds. These entities, like if I have, say, four or let's put six of these here. If this one's called A and this one's called B, A and B, in a sense, are always going to be holding hands, right? So they are stuck in place. But what's interesting about solids is these entities, they are not standing still. They're actually vibrating. So these little things are kind of like bouncing back and forth and vibrating. And they're all doing this. And the idea is as you cause this material's temperature to get bigger or warmer, these atoms and molecules and compounds vibrate even more until the temperature is so warm that they're no longer stuck vibrating in place. They start to wander around. And that's the situation of causing your material to melt. Yeah, and I'm sure you can internally think about this happening for ice. So for the case of ice, each of these entities would be a water molecule, and these water molecules would be organized so that they would be holding on to adjacent other water molecules. And as you cause the temperature of your ice to climb, right, increase the temperature, the water molecules would have a hard time holding on to their neighbors because they're being jostled around so much. And when one of them is able to break loose or leave the network, right, that, in this case, water molecule becomes part of the liquid, or maybe the gas surrounding the solid ice, right? So anyways, so this truly is what's happening. None of these atoms or compounds or molecules is standing still. What is sort of stuck is their locations and relationships to each other in a kind of a spatial sense. There's various different kinds of networks. So an example of a network could be a crystal network. And crystals are very regular organizations. Here's some examples. You could have a crystal network where each of the entities that makes up this material, like it could be a compound or an atom or a molecule, is like sitting at the corners of squares. But you can also have a regular organization that's a little bit more exotic. They're sitting kind of, they're making sort of, I don't know, on diagonals instead. And we could even have a crystal structure where something like this is happening, right? Which actually is the same as what I just drew. You can see that these two things are the same. In the case of water, water actually forms a sort of hexagonal structure that looks like this. So that's like a six-sided figure, right? And this is the origin of why water is able to form the snowflake shapes that it does, right? So this would be how water molecules network up in a. But these regular organizations, the drawings that I've drawn are two-dimensional, but really the regular organizations are happening in 3D, right? Because solids take up three-dimensional spaces. It's interesting to wonder, are there solids that essentially take up an area but only have, say, one atom of thickness? Yeah, and you might be starting to talk about really interesting carbon atom networks or carbon lattices. There are other structures. For example, metallic structures are a little bit less organized than the crystal structures, but those other structures lend themselves to, for example, in the case of metals, metals are ductile, right? And you can make wires, right? Or they're flexible. Let me just say that. Ductile and flexible. So you can take a long piece of metal and bend it and it won't break. There's a certain sort of brittleness to crystals. Like if you stress them too much, then they'll sort of crack and cleave along their crystal planes. These organizations lend themselves to saying something about the density and how the atoms are packed together, right? So the density is the amount of matter per volume, right? This is called the density. In particular, it's the mass density, it's called. Yeah, and that's an interesting thing to think about when you're thinking about atoms sitting next to each other. You can start to wonder how close are the atoms sitting next to each other, right? What sorts of distance is there? You can refer to as an interatomic spacing, for example. Okay, so just a couple more comments. So you can actually, without destroying the solid, you can cause changes in separation between adjacent atoms in a solid. And this change could be an elastic change. That is, when you stop causing the change, the material goes back to what it looked like before you caused it to change. And it can also have, in the alternative, an inelastic change. That means that, let's say you stretch something out beyond its elastic limit, then what you're left over with is something that's longer than before you did the stretching. So you kind of, in a sense, you reorganized how the atoms are sitting next to each other, or you damaged it in some way. You changed the shape of the thing. And these changes in separation could be a lengthening. That is, you take the two ends of the object, so let's say this is your object, and you apply a pull on either end. This is going under tension. And then alternatively, you can imagine there is the opposite, where you do a compression instead. And so the compression would look like where you took the two ends and you, say, pushed inwards on the right side, and you took the left side and also pushed inwards. And you might shorten the thing. Another interesting thing is you can also cause your material to change in size because of a temperature change. And the idea is that this has actually got a sort of technical description. It's called thermal expansion. Yeah, so when you warm things up, like say you take a solid object and you cause it to warm up, it tends to expand. But when you warm it up, you don't change the number of atoms, right? Warming it doesn't change the amount of matter. So if you get an expansion, what this means is that if the mass doesn't change, then the density decreases, right? So if your material spreads out and takes up a larger volume, and the density is the amount of matter per volume, and the volume gets bigger, but the amount of mass doesn't change, then can you see that the density is going to decrease? Because it's the denominator that's getting bigger. When you divide by a bigger number, you get a smaller answer, right? Okay, so those are some introductory thoughts on reading about solids, reading about the physics of solids. Okay,